So I thought a little bit, welcome back. I thought a little bit about the activity 3 yesterday. Before I want to briefly comment that that was the activity where you dug a little bit into thermodynamics, second law, enzyme kinetics, batteries, this kind of Raman thing. And I was surprised by, not by, you didn't do anything wrong, just the quality of the output was kind of low, right? I mean, we saw some pretty significant failures just getting consecutive numbers onto the JPEG or whatever it was. So I feel like reasons were probably twofold. The biggest one is, and this is really worth mentioning, if you generate an image, okay, the model behaves very, very differently. So what is happening during image generation, whether it's a cat or a scientific poster, is probably some primarily stable diffusion image generating algorithm. So, and you will still see wrong molecules. I did this 2 nights back. I was like, holy cow, there's a big benzene and one bond is replaced by a small, it looked kind of cute, right? But it's nonsense, right? So if you generate images, it's fine if it's something like that. If it's something scientific, it's probably not a good idea. So so keep that in mind. If you want to get good quality output, you have to avoid that path, right? And maybe hold the discussion before with the ChatGPT or whatever it might be on how to present it, what material to show, and then just you have to kind of provoke that it triggers Python and generates a kind of proper scientific figure. So that's one comment. And the other comment is, I think we also saw that if you are using Gemini, for example, or a free model, it's just cheaper and dumber. Okay, so you get what you pay for to some extent. Okay, so if it's free, you can't expect kind of world-class stuff coming out of this stuff. All right, let me dim the light. I can also do this here, and then we get started. All right, so today we will try to summon the ghosts and spirits, okay? So it will feel like that. It's really crazy. So you can do very fancy things with these large language models as it comes to data analysis. And so we will learn a little bit about how we can take real scientific data, even complicated data sets, and get some good analysis out of it. So that's what we'll be doing. I hope it will look a little bit fresher than these ladies and gentlemen. And so what we will be seeing and digging in today is machine learning, okay? That's the other big section of this lecture. And I hope that some human learning will happen along the way as I'm talking about machine. So let's start with the data analysis with ChatGPT, Claude, and so on and so forth. So there are clear pros and there are significant cons. And I want you to keep in mind that we are in a very moving, fast-moving landscape. And maybe it doesn't mean that much for it, but I want to say this anyway. So if you go back 40 years in computer science or 50 years, people programmed their processor with assembly, okay? So you told the processor, move this bit 1 over, right? This 1, I want 1 over. You were programming at that level. And it was very sophisticated and cool in the sense that you needed to know the architecture of your processor to do this efficiently, and then you got a really, really reliable, low, very troublesome but reliable results out of it. And then compilers came up, programming languages like BASIC is not a compiler, but Pascal, I want to say Fortran for sure, and C, C++, and so on and so forth. And people were not trusting these things. Okay, they're like, I don't know what this compiler is doing. I really need to see the assembly code, right? And today you will probably find no one that doesn't trust these compilers in 99.9% of all cases. So we are at a similar point, and we are using a new technology to analyze data, and it can be error prone, right? And you, like I always said, remain reliable and responsible for the quality of your results. So real quick, the process, you can do this in a neck-breaking speed, right? And get results out of it, especially if you know what you're doing. You get expert level summaries. And it can introduce you to new methods that you're not even aware about, right? This happens to me all the time. But there are also notable disadvantages, in particular that it's very hard to catch mistakes. So you really have to say, hey, show me the code. I want to verify a few things, right? Or maybe the whole code, right? So there's these pros and cons. By now you've probably read it. So let's get started. So this is a very simple example. This is Claude Pro, which level? Probably Opus 5. And I generated fake data. This exponential decay could come out of photometer, okay? Think of A as the absorption value, T as the time in seconds. So I generated that database before, and then I uploaded it by clicking on the plus button to Claude, and I said, fit the file and summarize its content, okay? And it gave me a summary of what it is. The file is a small 2-column data set, blah, blah, blah. This was all correct. And it started fitting, although I really hadn't asked for it, an exponential into the data set, which was a good choice. Then I said, okay, in the upper corner there, plot the data and exponential fit, report half-life with error. So that's the time it takes for the signal to drop to 50%. Wrong button. Explain error calculations briefly, okay? So it generated, again, within a second or something like that. It showed me the data. The red curve is the exponential fit. It even put the half-life on there. This is the half logarithmic representation of the whole thing. So this is the logarithmic axis now. This is the linear axis. And you see it's a nice straight line, like you would expect for ln x. And it plotted the residuals. I had added some noise to the data. And the residuals are how much you deviate from the fit. And you see they seem to be somewhat normally distributed around the zero value of zero residual. It also explained how the error was obtained, right? So when you look at the rate constant here, or the decay time, the half-life, it put errors on it. And you should always ask, where do these error values come from? And it gives us some information here on how it calculated the whole thing. Okay, so that's a very simple example. I think many of us are fitting an exponential at some point, or early or late. But you can also do a lot of image processing. And I should quickly mention, none of these things are revolutionary new, right? It's just convenient that you can, in English, interact and ask for this. There are programs for this that your group or future group might be using. And it's equally fine, but it's kind of convenient. And it's only, this stuff can do much more complicated and tailored things. So this is an SEM picture that I took from a paper. I'm citing it down here, and I didn't tell ChatGPT what paper that came from. Claude. And although you don't see it here, the thing had a scale about 500 nanometers. And it shows nanoparticles in a TEM image, right? Transmission electron microscopy. So I say, find the nanoparticles in the TEM image, create an image that superposes each particle boundary as yellow lines, okay? So a millisecond later, this popped up. It had nicely found most of the nanoparticles. It did not like this one here because they're closely touching. They also look a little odd, to be honest. So it didn't analyze this. And again, unprompted, it gave me kind of a summary of what I'm seeing, 269 particles, right? This and that. And it gave me the equivalent diameter in nanometers using the scale bar, although I really hadn't talked about it. The size range, the coefficient of variation, aspect ratio is close to 1. They're somewhat spherical, area coverage, and so on and so forth. So you can do really cool things like that in no time. Then I said, okay, do your results match those in the paper? So I now revealed the paper. I wouldn't bet my life on it. I didn't know the paper, but probably not that one figure. And it said, yes, closely, once methods are matched. And it gave me this table. So this was the paper result. This was the original pipeline. We just looked at the results. And then it had, in that split second, read the paper, programmed the analysis method that the paper suggested, and recreated the analysis results from the paper. They match somewhat, but not perfectly, but that's fine, right? All of those numbers are very similar. So kind of remarkable, I think. Here's the thing. I'm not a big NMR user, but I randomly stole a 2D NMR spectrum from the internet. And it didn't have any, as far as I can tell, much text information. So I said, what can you tell me about this? Okay. And this is a picture, and that's where I got it from, Colombia. And it said, oh, this is a 2D homonuclear proton-proton correlation spectrum, almost certainly a COSY, and so on and so forth, right? So, and then it said, oh, it's probably sucrose, right? Why is it sucrose that we are looking at? I don't know how many people of us would have figured this out. Some expert probably would have seen it immediately, but and of course, this is from the web page. It is a COSY spectrum of sucrose. Okay, next step. And the last thing also showed you the power. If you don't understand a figure, you can just upload it and talk with it about it. So you can also run numerical simulations on Claude. This is a little bit longer prompt that I'm giving here. And so I give fairly specific instructions. I provide a diffusion coefficient, initial condition, stuff like that. And I'm essentially asking it to integrate numerically this differential equation here, which tells you how fast essentially ink spreads out by Brownian motion. Initially it's a nice spot, and then it kind of smooths out over time because of the motion of the molecules. So that's not a super hard numerical problem, but it's a partial differential equation with some boundary condition and initial condition. So, and again, within a split second, it generates this diagram. This is space in centimeters. This is a concentration. This was the initial condition that I had asked for. And you see how the curve slowly goes down and spreads out. The area underneath should be constant. I think it is. And then it talked with me a little about here what the numerical parameters were and stuff like that. So 2 quick comments. So this demonstration for the first time very, very clearly shows that Claude has actually a computer at home, okay, and runs this simulation on its own computer. So it's not running it on your computer. So it has a sandbox and has a CPU there, and it creates a Python script and it runs it, okay? And then it looks at the outdate and displays it for you. So that means it has the limitations. I, for example, asked, can you do a density functional a DFT calculation, right? And said, yeah, I can do that for you, no problem. But please keep in mind, I have only a CPU and this isn't much available, right? So we are limited in the size of things we can do. The other thing is, I think, kind of peculiar. For whatever odd reasons, it switched to British spelling. No, sometimes. Oh, they're an American. They're an American company, and this randomly switched occasionally to British spelling, Amy. Actually, I never happened to see it, that the thing, even when you look at the thought process that goes through, switches to other languages like Chinese. And so don't ask me. Okay, here's another thing. This is from Wen's research, or related to it, I should say. It's not her work, but a postdoc advisor from Berkeley, Judith Klinman. And that is actually something we downloaded from her paper. It's supporting information. It was an Excel spreadsheet with many sheets inside and really lots of data. And so I uploaded it, and I think I asked, what can you tell me about this data? So a couple of interesting things happened. The data had the article number, right? Not the publication information, the article number and JAX in it. And it immediately associated it with the paper, which I didn't quite see coming, okay? And then it looked through it, and it told me a little bit what's in this complicated paper and how it relates to SI figures and stuff like that. So surprised me a little bit. The 2 of us actually dug into this or similar data, and at least for a little while, we were very, very impressed, right? Okay, so here comes something else, scraping data from other papers, right? There's nothing illegal as long as you follow all the rules. So this is an EPR, electron paramagnetic resonance study, of the reaction between a cerium-4 ion and malonic acid in an acidic solution. And the cerium-4 ion comes and grabs an electron away from the malonic acid, creating the malonyl radical. Okay, so it is a free unpaired electron. And these radicals you can see nicely in EPR spectroscopy. Okay. Now, the problem is they're very short-lived, right? These guys want to find something to react with. They're highly reactive usually. And so these authors in the 90s, early 90s, set up a flow system. So they flowed in the cerium and the malonic acid solution, ran it through the EPR cavity in a quartz reactor, right? And could essentially stabilize the radical, right? You flow it through, you get a static situation in the at the measurement point, and you can nicely characterize the radical. Now, if you flow a little slower, you dial into a later stage of the reaction. If you flow a little faster, you see the fresher reaction system, so you can very systematically probe the kinetics. And without going too much into the details of this experiment, that was the data, and these were the plateaus for different flow rates, pump rates, okay? Here we were pumping fast, and we saw the fresh early reaction. Here we were, or not we, they were pumping slower, and they got a little bit less. So this is pre-PDF, so this was scanned probably around 2000. So it's really, really bad quality. I hope you all see it, right? And then the data is also kind of a little iffy, right? And so I asked it to extract the data with one short prompt. And I magnified it here a little bit. I think it did a pretty good job extracting the data from the image. And then I said, okay, these are plateau values. Extract them for me. This is the pump rate in milliliters per minute. This is the extracted concentration in micromolar. And two of those values were mentioned in the paper, and they match up pretty nicely. And this is like short prompts, right? I got this. It's not like a half-hour process. So then I asked it to plot and fit the kinetics, and it generated within a split second this thing for me. And it gave the right experimental rate constant for this condition. So we went from this kind of really old, I was not that confident that this would work, to this really, really nice looking result. So it shows you can do amazing things with Claude, right? But I'll now move on to the second part of my lecture, and that is machine learning. Okay, so these were pretty conventional analyses, and they're very useful, and I think many of us will be doing them and continue to do them. But an important part that we want to talk is about machine learning. And there are things like supervised and unsupervised learning. So I want to introduce a little bit the vocabulary, and then I'll show you examples. So I touched on this already yesterday, what AI is. And AI is this whole big bubble of things that are out there. And within it, as a subset, resides machine learning. So machine learning is essentially where we said, like we said yesterday, where an algorithm computer looks for patterns in your data, okay? And there are different ways of learning or training this machine learning system. Supervised learning, unsupervised, self-supervised, and reinforcement learning. Another subset is deep learning, and we'll be talking about that with neural networks and stuff like that in the afternoon. So the big take-home message, I definitely want you to get the difference between supervised and unsupervised learning. So supervised learning sounds like you are doing something, right? And to some extent you are, but it's really more like I have a data set, and it could be an image or a vector or Excel spreadsheet, and I say that spectrum is that molecule. So you have the data and you have the label, right? The name of the molecule. So when it starts learning it, it tries to associate the information with the molecule or the picture with the cat and stuff like that. Now, unsupervised learning is weird. You don't tell it what molecule it is. You just provide a whole bunch of cat pictures or animal pictures or spectra or whatever your data might be. And you're like, try to find something in there, find a pattern, okay? But you're not providing really the information, perhaps because you don't know what that stuff is. So you can think about it like this, just to say it again. I know the answers here, right? My data are red, green, and blue, the colors of the chemical, whatever it might mean. And now I give you an unknown sample, right? And I ask you, what's the color? Okay. And it will say, okay, I've never seen this, but it's green. That's my guess. In unsupervised learning, you just don't give the color information. You just like, look at all this data. Do I have groups here, right? And might say, oh yeah, I have this group and I have that group, right? And when you look at it, you might actually see that it correlates with something in reality. And then reinforcement learning is a little bit what like Dr. Nakuzi talked about yesterday, where you tell an autonomous AI system with, with instrumental access do the experiment, or it tells itself, I will do this experiment now. I look at the result. The result is not what I want. I have to change it, okay? And the changing is done with reinforcement. So you punish or reward the system. And I think in in this literature, they mainly talk about reward, but a punishment is a negative reward, okay? So this is the little attempt to visualize this ecosystem of machine learning. And there are really applications across the board, not only in chemistry, of course, but if you fly international, you don't even show your passport anymore, right? Your screen. This stuff is probably machine learning. And okay, so we want to now go through the workflow. What you need for machine learning is some data. If you don't have data, you have to either download it from someone or you have to generate it yourself. That's probably what you will do. And you have to define a task, what you want to accomplish. Then you train the machine learning algorithm, whatever it might be, on that data, freeze a little bit of your data for testing, right? And you don't want usually, you don't want the system to see that data before, right? So you task definition, training data, choosing the model, training the model, and then do inference. That means you ask a question. You haven't seen this. What is it, right? So that's the kind of the goal. And so here's an example. This is pretty seemingly well-known data for educational purposes, primarily 1,000 chemical compounds, or 900 something. And they aim at solubility, okay? Is this stuff soluble in, I think, water? So you have this big data set. We can look a little bit into this. It's freely available, right? We have it on Teams. And look at these different Excel columns. And column A is important. That is the label that I was talking about, the cat, the rat, whatever. So this is a compound ID, meaning molecule name. That's our label. Then an interesting column is column D. That's the molecular weight in grams per mole. That in the beginning will be our X coordinate, okay? So we're plotting against molecular weight. And then we have H bond donors, numbers of rings, polar surface area. That's interesting. And for the time being, we'll focus on measured log S, where S is the solubility. But the logarithm solubilities change a lot, right? Not by a few percent. So we take the logarithm. And that is that column here. And you can see the numbers can get negative because of the logarithm. So that will be our initial Y, okay? X molecular weight, Y solubility, but on a log scale. So this time I used Gemini, and this was in April. So I said, okay, take that data, I uploaded it with a plus sign, and I said, well, plot the log solubility against molecular weight. So we get immediately an idea about what our data looks like, right? And then I said, okay, do a linear regression. Bang, there's a line. Okay, so, okay, not great, not a disaster, right? Because solubility is a bit more complicated concept. And that regression line, in a certain way, is already a model for the data, right? Because I could now make a prediction for an unknown compound by just using the red line. But you will immediately see or feel that it will not be a great prediction, right? But it's some prediction. So that would be supervised learning. Unsupervised learning would be, let's say I plot the molecular weight versus the polar surface area in square angstroms. And I don't even say what these molecules are or whether they're poorly soluble or highly soluble. And I plot all this stuff. And initially, there will be indistinguishable points. And now I say to Gemini, well, do a cluster analysis. Do K means clustering. We'll talk a little bit about in a second. And it says, oh, okay, I think I see 4 clusters in your data, and I will color them differently, okay? Now, you have no physical insights what they are, but when you start interpreting, you see that some are more greasy, some are small, simple organics, others are large and very polar. So you can kind of start interpreting your data a little bit. But you see, you gave the information, the unsupervised machine learning system, very little information. All right, so why is this machine learning? It sounds we think of language translation, all the fancy things, right? But again, our linear regression gives us a model for our data. You don't usually think of linear regression as a model, but it is a model of your data. A bad one, but that's a different story. The unsupervised learning, so I can plug in a molecular weight and it will give me a prediction for my solubility, a numeric, quantitative, continuous value. If I do this with the k-means clustering, the unsupervised learning, all I get out is a classifier. So a classifier is a discrete thing. It says, that data point you just showed me, I think it belongs to group 1, okay, or cluster 2. So that would be the unsupervised learning. All right. Then just very briefly, what Elias talked about yesterday afternoon, reinforcement learning. I don't want to make it too complicated, but let's think retrosynthesis, a topic I feel very uncomfortable talking about. You have a target molecule, you pick a disconnection, reverse reaction, and then if you reach viable starting materials, you give a reward, and you have a policy, essentially which disconnection to try. And again, punishment is just a negative reward. So you run through this loop, the system optimizes this for you, and then it's good or not. All right, here's a summary of it, 3 robots. The first robot says, it's represented supervised learning, they gave me so much to read and test, right? The unsupervised robot says, me too, but at least they told you the answers. And then the reinforcement guy says, at least you all don't get punished for every wrong action, okay? So these are the 3 main parts of machine learning. All right, so now I did this with Claude for the simple examples that I showed you in the beginning. I want to now do this with our solubility data, and I want to train and test our data for picking predictions. So the first thing that you usually do is you split your data into training data and testing data, okay? And the split is usually an 80-20, 70-30 split, something of that sort. You have more training data than testing data. You do the split randomly, right? So that there's no bias in this process, or you definitely try to minimize any bias. So bigger data helps, right? And then maybe as a very technical comment, often you should try to set a seed for the random number generator, because random means that the computer generated random numbers, and it's great, but maybe you want to go back and do the same thing again. So you can seed the random number generator with a number, and the next time you run it, you will get the same result, okay? So sometimes you want that, sometimes you don't, but usually you want to be always able to go back. So very important, and this gets very tricky, and there's already a lot of wrong stuff in the literature, I think. You have to make damn sure that the testing data has no information about the training data, okay? Otherwise, you can very easily trick yourself and others into believing high quality outcomes, but some information leaked over, and it can be very subtle. It can be very subtle. Right, so the other thing we are doing is when you look at these numbers in the Delaney solubility data sheet, you already see that there were vastly different ranges of numbers, right? Molecular weights, well, there's small numbers between 100 and 1,000 or whatever. I didn't look at it. I think I can, but 800. And so they're fairly small range. The solubility changed on a log scale, right? Other numbers changed greatly. So you want to make sure that all of these number ranges in most analyses are kind of normalized, right? Otherwise, the algorithm might think, oh, this changes so much, I want to emphasize this, but just a numeric scale thing. So the procedure for that, and it's very important, it's called z-scoring. And the idea is you have your distribution, this is just a histogram of molecular weights, and you calculate the average, the mean value of this distribution, and then you subtract it from all the data. So the new data set will have a mean, an average of 0, right? And then you do another thing, you divide by the standard deviation, how wide the distribution is, even if it's not if it's not a normal distribution. So this has a certain spread here. And you see here, the standard deviation is suddenly 1 because I divided by it. So the z-scored data is a data set that distributes its data around 0. And it has a width, a standard deviation of 1, okay? And now they're all on equal footing, and you can compare them more easily. So that's called z-scoring, and it's a concept that was used before all of this. All right, just as a reference point, within the 1 sigma interval, you have about 2/3 of your data. Okay. All right. Data leakage warning, I gave it to you already. Make sure that there's no data leakage, information leakage. So making predictions. So I go back to my linear regression model, okay? So I split my data 80-20, 80-20, right? I plot log solubility against, no, so this is a little different. This is the measured solubility from the data set, and this is the predicted solubility for the test data. So first I train, I make the linear regression, then I have this other 20% left, and I test how good my predictions are. And you see they're not great. So you can look at ideally you want everything on the diagonal, then every prediction is right, right? Every original real value is identical to the predicted value. You can look at the differences, the residuals, how bad your distribution is, how prediction is, and plot this. And you see it's kind of nice that it's at least centered, so we didn't introduce a bias. We are still around 0. But the width of this distribution is such that it's about the equivalent of, in real solubility, not log scale, a factor of 50. So you're often off by a lot, okay? Not a good model, but it shows you in a simple model how this stuff works. All right. Now I said that everything we are doing here, which looks like summoning ghosts, right? In reality, ChatGPT or Claude start to write a program for you. And it happens in a tenth, hundredths of a second. It generates a program, runs it on its own computer, and then spits out the result. So it's a good idea to once in a while look at this. I guess at this point in time, I have to say it's always a good idea to look at it. I think in 5 years, we'll be like, you remember the times when we looked at the program? So, but in the moment, we have to look at it. And this is a Python script Gemini wrote for our analysis, right? And I don't want to go into the details. I promise no programming. But you see here's the linear regression happening, right? All of this here is essentially just graphical output. It generates a figure, but not like the stable diffusion, like I think what happened yesterday, but with a real rigorous approach. So no magic. It's writing a code and runs it on your data. All right. The next thing I want to talk about, this was just linear regression, as a simplistic example of machine learning, right? So we want to do something slightly fancier. And a technique that my postdoc and I really like are decision trees and random. Okay, so they work very well for our data and they have certain advantages, but they have, like everything, also disadvantages. So what's a decision tree? Let's say for the solubility data that I showed you, the question is a given compound that I present soluble at 1 millimolar? So I provide all the polar surface area, molecular weight, and I say, is it soluble or not? Okay. So then the decision tree program, the program that decides, creates a decision tree, makes a criterion. Like here, it could say, oh, I looked at your data. If the log S is greater than -3, then it's a yes. If it's smaller, then it's a no. Soluble, not soluble. Now, the problem is this example is trivial, right? Because 1 millimolar, 10 to the -3, log is -3, so I will always be right. So I showed it the answer, right? So that was a trivial example, but that's how a decision tree works. So I asked, I think, Claude to take the Delaney solubility data and create a decision tree for it. And it came up with this. And not only did it did not only write the program, ran it on my data, it also created this slide. The only thing I changed was that I wrote and made the slide, okay? And I don't know how long it would take you to make a slide like this, but it would take me a little while, right? So what's this decision tree it cooked up? It said, well, the question is still 1 millimolar solubility or not, right? First, I look at the molecular weight. If it's smaller than 222 grams per mole, then I go down here and I ask now for these small molecules, is the polar surface area less than 6 angstrom squared? If no, right, then I predict that it will be soluble, solubility greater than 1 millimolar. So you go down these different paths depending on what molecule you have. And the wonderful thing about this decision tree is you can still rationalize it, right? You can say, oh, does this make sense? Yeah, I think it makes sense, right? And like if you have a very big molecule, you're already on the left side, it's less likely, right, to be soluble. And so I think that's very cool. There are algorithms behind this, mathematical algorithms that I will not discuss. So this is not a unique tree. Other trees could have been generated, okay? But that's how that works. A little bit of nomenclature. So this is a decision tree. And this is a decision tree with 7 visible leaves. And the leaves of this decision tree are these 3, 4, 5, 6, 7 endpoints, okay? And you can build a decision tree that fits your entire data, no matter how big, okay? But you can imagine it gets very, very intricate because it has to kind of build a little box for every data point, right? So you want the decision tree to still be compact, and this process is called pruning. Okay, so that's how that works. And the algorithm ChatGPT used for this decision tree is a card decision tree classifier. So again, you could look at the program and everything and run it separately outside of it. The other thing I forgot to mention, it works pretty well. 85% of the time it gets it right? Much better than the linear regression that I showed you before. Okay, so that's a decision tree and one possible algorithm, name. But there are also other possibilities how you can extend this. And one is called random forest. It's a very frequently used machine learning algorithm. So we see that we can construct these trees, like tree 1 we might have just looked at. But I told you it's not unique, right? There's not a unique best tree. So you could have created other trees. And in the random forest algorithm, you say, hey, create, for example, 1,000 trees for me. Okay, they're all a little different. And then you train your random forest algorithm on the outcome of predictions. And the way this is happening is that every tree casts a vote. I say it's soluble. I don't think it's soluble, and so on and so forth. So you get 1,000 votes in, and there's a winner. It's either soluble or not. Okay, and that's a random forest prediction analysis. In this particular data case, it really didn't change it much, right? We went from 85 to 89. I didn't repeat it. I should probably put an arrow on it and stuff like that. But there's a small improvement. But we went from 1 tree to 1,000. We didn't get a lot of it out of it, right? So that's random forest. Makes sense? Basic idea. Okay, then the k-means or k-nearest clustering algorithm is another one. This you can do too. So here's the polar surface area. Here's the molecular weight. And the way this algorithm works is you give a target molecule, like I want to know the solubility of caffeine, okay? And it will say, in my data space, the Excel rows, where you have polar molecular weight, polar surface area, and so on and so forth, I plot this essentially as a point in a high-dimensional space, and I find the nearest neighbors, meaning the molecules that are most similar with respect to my data set. And I take k of those nearest neighbors, usually a fairly small number, like 11 or so, and I take these 11 neighbors, and I see whether they are soluble or insoluble. And then I have these neighbors vote, and the winner takes it. And in this case, there are more blue dots where the solubility was greater than 1 millimolar than red dots, and you cast the vote. And in this approach, you get 88.5%. So all comparable. Makes sense? So the similar data points or vectors in your data set vote on the outcome. All right. Another thing, pairwise solubility classifiers. You can just ask the question, is molecule A more soluble than molecule B? Right? That's often an interesting question. And so the way the result is then reported, and the result is maybe a little less good, but it's a different question we are asking, is shown as a confusion matrix. And I show this slide mainly to introduce what a confusion matrix is. So this is it's plotted here. This is the reality. It's true, okay? This is the true reality of it. And this is what you're predicting, the x-axis. So again, ideally you're on the diagonal, because then the prediction and the truth, the ground truth, are the same, yeah? But in this particular case, the diagonal is pretty nicely populated, right? Most of the time we get this right. But you can also see the outliers, okay? And these two numbers are not the same, although often similar, because they're slightly different questions, these off-diagonal elements. But let's not go there. But you get the idea of a confusion matrix. And this is a 2 by 2. These things can get big, right? So there you have it. So that's a confusion matrix. we will ask you to create one later on, I think. All right, so that brings me to the summary of this talk. So we learned a little bit about using ChatGPT and Claude for data analysis. I hope you were as impressed as I am. I know you have less of a reference point. It blows my mind, right? We talked about machine learning, that it can see patterns in data sets. We introduced definitely the difference between supervised and unsupervised learning. We looked at an example thing and showed that linear regression was classifiers is a thing. Decision trees, random forest, k nearest neighbors, and confusion matrices. So these are the things I hope you got out of this lecture.